Last time we talked about lines in space, and to come up with the equations for a line in space, we needed a vector that was parallel to the line. For a plane, we're going to use a point on the plane or in the plane, and a normal vector. We need a normal vector for our plane. So let me draw a little picture here of our plane. So here's a plane in space. And we have a point on that plane. We'll call it P. There's P, point P. And we're going to draw a vector in the plane. There's Q. So we're going to say P is point x1, y1, z1. So that's a point that we know is in the plane. And PQ is in the plane. So Q is just some arbitrary point in the plane. And here's our normal vector. There's a normal vector to the plane. I'm going to say that's n. And this is a 90-degree angle. Those two vectors are orthogonal. The vector is normal to the plane. N is orthogonal to PQ. And we're going to say n in component form is the vector ABC. So there's our setup. What we're going to do for our purposes is we're going to define the plane as the set of all points Q, and we're just going to give some arbitrary coordinates to Q, so that PQ dot n equals 0. So we're going to define the plane as a set of all points Q so that the vector from P to Q is orthogonal to the normal vector. And that's going to give us a plane. So we just some point in the plane, as long as the vector from P to Q is orthogonal to the normal vector, we're going to be in that plane. All those points are going to be coplanar. This is the vector equation for a plane. Does that make sense, that why we could define a plane that way? All those, no matter where we draw that vector from P to Q in the plane, as long as those are orthogonal to a particular vector, they're going to be coplanar. All right, so this is going to be this is nice, but we want a different form. It's going to be more useful for what we're going to do. So this tells us that the vector PQ is x minus x1, y minus y1, z minus z1, dot ABC equals 0. And then we can form this dot product, and we get a x minus x1 plus b times y minus y1 when we do this dot product, plus c times z minus z1 equals 0. This is our standard form for the equation of a plane. And it contains the point x1, y1, z1 with normal vector ABC. And we could multiply this out, and we get ax plus by plus cz plus d equals 0. And the d term contains all the constant terms from this. So this contains all the constant terms. And if we think back to Algebra 2, when we solved, or we did it in pre-calc as well, when we solved systems of equations, when we did the 3 by 3 system of equations, our equations always looked like this. And when we're solving a 3 by 3 system of equations, we're finding where various planes intersect. And when the planes intersected, when we got an infinite number of solutions, we just wrote an infinite number of solutions, because writing the equation of a line in space is, we know now, is a little more involved than writing the equation of a line in the plane. And again, here we can, from the coefficients, we can pick out the normal vector to the plane. So when we're talking about our 3 by 3 system of equations, the coefficients on our variables were the normal vectors to those planes that we're trying to find the intersections of, were the components of the normal vector. All right, so we're good with our equations. Normally, we'll see an equation of a plane that looks like this, or that looks like this. Notice that all the terms are linear. So the equation of a plane is going to be some kind of linear equation between the variables. All right. So we know that two distinct planes, they either are parallel or they intersect in a line. Well, sometimes we'll be interested in the angle between planes. So what we're talking about is if we had a plane like this, I'm going to draw a picture here, like that. So here's one plane, and it's going to intersect another plane back here, like so. Those two planes are going to intersect in some angle, or at some angle. We can figure out that angle of intersection because if we draw the normal vector to this plane, I'm going to draw it like so. I'm going to call that N1. And I can draw the normal vector to this plane like so. Oops, let me change the color there. And I'll call that N2. The angle that the planes intersect is the same as the angle at which the normal vectors intersect. Thank you.
I need to learn how to draw.
So we can say the angle between the normal vectors is the same as the angle between the planes. And so we can say that the cosine of theta is, and we want our angle to be acute. Not acute, between 0 and 180. So just wanted to make sure I was, so we're going to say the absolute value of n1 dot n2 over the magnitude of n1 times the magnitude of n2. We can find the angle between those two vectors, and we want our angle to be between 0 and 180. Well, actually, if we take that, no, that's good, yeah. So we want our angle to be between 0 and 180. So that's going to be our angle. That'll give us the cosine of the angle. The cosine of the angle between the two normal vectors. And we know that if n1 dot n2 equals 0, then the planes are, their normal vectors are orthogonal. The planes are perpendicular. Isn't that nice? We use all three words for 90 degrees in one sentence. We said if the unit vectors are if the normal vectors are orthogonal, then the planes are perpendicular. Yeah. Yeah, Kyle is seething with anger right now. If n1 equals some scalar multiple of n2, then what's the case there? The planes are parallel.
See, there's only one word for parallel. Why is there multiple words?
Yeah, I was thinking that it wouldn't it be nice if there was a different word for parallel.
That would not be nice.
Yeah.
Wait, is that
Oh, this should be an equals, yeah. I said is, and I wrote a
How
dot.
about scalar coincidence?
How about
Scalar coincidence, then they'd be the same plane,
No,
right?
scalar coincidence, it could be coincident divided out. So there is another word. Nobody.
All right. So the normal vectors to planes give us give us all the information that we need about a plane.
you don't explain to me the normal vector?
The normal vector is the key piece of information about the plane. And we can use that normal vector to find the distance between a point and a plane. And if you remember, when we talked about the distance between a point and a line, we used a cross product. So let me draw a picture here. Here's our plane. Whoops. Here's a point on the plane, P. Here's a point that's not on the plane, Q. And here is our normal vector. So there's n. And the distance that we're interested in is this distance here. So here's what we're going to do to find that distance. We're going to draw a vector PQ. Let me do that in a different color. So there's vector PQ, and I'm going to project this over here, like so, where that's a 90-degree angle. Well, this distance is also d. So we're going from the Q straight down to the plane. So this is a 90-degree angle here. Yeah. So we're going straight down. We're going straight down from Q to the plane. So that's our distance. We want our distance to be the perpendicular distance, the shortest distance. And I'm going to call this angle theta. Well, what do we have going on here?
Triangle.
We have a triangle. We have that this distance, d, is the magnitude of PQ times the cosine of theta.
Wow.
Well, what is this a piece of?
Projection.
That's the magnitude of the vector projection, right? This is the magnitude of the projection onto the normal vector of PQ, and that vector projection, and we can also think of this as a portion of what? So I'm going to write down here and n dot PQ is the magnitude of n times the magnitude of PQ times cosine theta. So the distance, this is PQ cosine theta, that's this quantity divided by the magnitude of n. So we get the distance is n dot PQ. And I'm going to take the absolute value because we want our distance to be positive over the magnitude of n. So we can use the dot product to find the distance between the point and the line. Or the plane, sorry. We use the cross product to find the distance between a point and the plane, or the line. So what we're saying here is P is in the plane. And Q is a point not on the plane. And n is the normal vector to the plane. So that normal vector, again, is the key to finding that distance.
So wait, is the normal vector, since planes are infinite, how can we find the length of the normal vector, like the magnitude of it? Because shouldn't it?
You can just find a normal vector.
Oh, so it's any normal.
Any normal vector,
So
right?
you could just use one and say there's a unit vector that's.
Yeah, you could find the unit vector normal to the plane, but you don't have to. You don't have to. You can use any, as long as it's normal to the plane, you're good. All right, so let's look at a couple of examples.
That makes sense. Straight up. But what about this?
It's just a relationship. It's like, which one is
So let's find the equation of the plane containing negative 3, 0, 7 with a normal vector um, 5, 2, negative 1. So when you see a problem like this, really you have everything you need. So what would be our equation? Can we pick it out? We have 5. These are going to be our coefficients. 5x plus 3. X minus x1 plus 2 times y minus 0, I'm just going to write it out explicitly, y minus 0 minus 1, to be explicit, z minus 7. And that equals 0. You have to have the equation. To write the equation, you need an equal sign, so equals 0. You could multiply this out and combine your constant terms. You'd get 5x plus 2y minus z equals negative 21. That would be the equation of that plane. Nice linear equation in all of our variables. Yeah. No, it'll just, usually the question will say, write an equation of the plane. Yes? Is it 22? 15 plus 7? Yes. 22. So to sketch, and I was going to say they go into a little more detail on page 787. Talks about sketching planes.
Do we need to know how to do that?
Yes.
Wait, we have to sketch planes? Like,
We will be sketching lots of different surfaces. So to sketch this plane, what we're going to do is draw a three-dimensional coordinate system. And then say when x, or when y and z equal 0. So when y and z equal 0, where are we? On the x-axis. When y and z equal 0, x equals negative 22 fifths. So we'd have a point out here at negative 22 fifths. Then we'd say when x and y equals 0, z equals 22. So we'd have a point up here at 22. And then when x and z equals 0, y equals negative 11. So we'd have a point out here at negative 11. And then we connect those with a little triangle. And that's where the plane intersects the fourth octant, which kind of slice through that way. So that would be a sketch of that plane. Just that little triangle. So the plane is in space, and it's slicing through our coordinate system there.
so do you not need to draw all?
No, you just need to draw that little triangle. And it would
So it's basically just sketching a plane. So sketching a triangle and labeling.
yeah, yeah.
And
So on page 287, it explains that process in a little more detail. But really, that's all there is to it.
why are the 22 bits and 11 in space, like in the x plane and not on the axis? Like,
No, this is my negative. This is my negative x-axis,
oh,
and this is my negative y-axis.
Okay, yeah.
I just drew them dotted.
Yeah,
Okay. So yeah, this continues that way.
yeah.
That continues that way.
I was-
Okay. All right. What if we wanted to, we're not going to go through the whole process, but let's talk about it. How did we find the equation of an equation of a plane? How many points does it take to determine a plane? 3, right? We need 3 points. 3 points to determine a plane. So let's say we know that it contains 0, 0, 1, 2, 0, 0, and 0, 3, 0. So there are 3 points. We want the equation of the plane that contains those points. What do we have to do? Well, what do we need? What's our key piece of information? The normal vector. How are we going to find a normal vector? Make 2 vectors and take the cross product. So I'm going to call this A, B, and C. And our normal vector is given by, or a normal vector is given by vector AB cross vector AC. And we can make a vector between any of those two, any 2 points and do the cross product. So that's going to give us a normal vector. And then we need a point on the plane. Well, we have 3 to choose from there. So we can write your equation with any of those 3 points. So we're don't need to go through the process. I just wanted to think about the process.
That's a good idea. Just guessing.
Just guess, right. It gets a lot more difficult in 3 dimensions to guess correctly.
Yeah, because now you have to give more parameters. Any guessing is not
Let's look at a distance problem, and then I want to give you a different formula that you can use for distance for those of us that like to memorize formulas rather than thinking about the dot product, which is much more intuitive and tells you more about the geometry that's going on there, which is going to serve you better in the future. But find the distance between point Q, which is 1, 1, 3, and the plane, 3x plus 2y plus 6z equals 6. All right, so what do we need here? What's our key piece of information? Our normal vector. N is just the coefficients on my variables, is going to be 3, 2, 6. We need a point in the plane. How are we going to find a point? Plug in a couple of zeros for our coordinates. So plug in, I said let y and z equal 0. So I get x equals 2. Yeah, you could choose any pair, set them equal to 0, and solve for the third. So our point, in this case, a point on the plane is 2, 0, 0. So then my vector PQ is, in this case, there's Q, so PQ would be negative 1, 1, 3. And my distance is the magnitude, or the absolute value of n dot PQ over the magnitude of n. And so we get the absolute value of n dot PQ is, what do we get? Negative 3 plus 2, 17, plus 6, 17, absolute value 17 over the magnitude of n. Square root of 9 plus 4 plus 36, which is 7.
Yes, dude. Oh my god.
So the distance is 17 seconds, units. All right. So if you like to remember formulas, we can say that if we can use this dot product to write that our distance equals A x0 plus B y0 plus C z0 plus D, absolute value, divided by the square root of A squared plus B squared plus C squared, where Q is given by x0, y0, z0. The plane is ax plus by plus cz plus d equals 0. And in this case, d would be negative ax1 plus by1 plus cz1, where p is x1, y1, z1. So you can memorize this formula, or you can use this formula. I think this is way easier.
So you just use force formula versus the absolute value and square roots.
Yeah, the absolute value, this square root is the magnitude of n, and this pq dot n absolute value turns out to be this thing. All right, the last example I want to talk about is the one I want everybody to be very careful with, because this is often one that students like to forget.
I'll forget it.
We want to find the distance between the parallel planes x plus 2y plus 6z equals 1, and x plus 2y plus 6z equals 10. And I'm going to say it's not 9. And the reason it's not 9, or it's not necessarily 9, it could be. The reason is we could have our planes like this, and we're interested in this distance, and not, we're interested in that distance, not this distance. So that's the vertical distance, but in this case, the vertical distance between those two planes could be 9 units, but we're interested in a perpendicular distance.
Is the perpendicular distance 9 now?
No. So what do we need to do? Well, so what we're going to do is we have two planes, but what we're interested in is the distance between a point on one plane and the other plane. So pick one plane to be the plane. That's the plane that you're interested in. So let's pick the first one. So let's let x plus 2y plus 6z equals 1 be the plane. Well, what is the other plane going to give us? A point. So we're going to use the other plane to get a point. I'm going to say a point Q. So on the other plane, let's let y and z equal 0. So Q is the point 10, 0, 0. And we also need a point in the other plane. So we want a point in that plane to make our vector PQ. So what would be a convenient point? 1, 0, 0, right? Plug in y equals z equals 0. And P is 1, 0, 0. And our distance, so PQ is the vector, in this case, negative 9, 0, 0. We could also use QP. We just get it because we're taking the absolute value at the end anyway. And our distance is the magnitude of PQ dot n. What's our normal vector for this plane? 1, 2, 6. Well, that's the normal vector for both planes, right? Since they're parallel. And is 1, 2, 6. So our distance is the dot product here. Look how nice this turns out. The absolute value of negative 9. There's that 9 that we were talking about. Over the magnitude of n. Square root of 41. So our distance is 9 over the square root of 41. So a little smaller than 9. Approximately 9 to well, square root of 41 is what, between 6 and 7? So yeah, but 9 would be pretty small, far off. Yeah. That's kind of the same as when we were talking about series, when we decided 0 equals 1.
0 is 1 though. Like that's just factual.
I mean, yeah.
We would have to do an actual word.
All right, questions there. Make sure you look at that page in the book about sketching planes, because you will need to know how to sketch planes. What we're going to do next time is start talking about visualizing surfaces. We're going to spend a couple lessons of talking about surfaces in space. Tomorrow we'll start with nice easy surfaces, and then we'll get into a little more interesting surfaces on block day.
So is the sketching plane stuff basically you plot points
On the axes and make the little triangle. Yep.
So basically you could just draw a triangle and label it
Well, you have to make sure it's in the
in the right
quadrant or right octant, right?
As long as it's in the right orientation, of X, Y, and Z, you're okay. Because it's sketching, you don't have to be absolutely specific.
Ooh, good shot, Kyle.
There we go.
Drop it